A decision tree example in Scikit-learn. Please download the IPython files and open the template file and follow along. We're going to work with the iris dataset. As we have seen it before, you are familiar with this dataset. And happy coding. Similar to always, we start with importing the libraries. So we're working with iris dataset, so we're going to import the load iris dataset. All right, that's the only library that we need so far. Let's import the data, load the data. So I'm going to call the data iris, and then I'm going to call the load iris to load and make a copy of the data. So just as a reminder, we're going to take a look at the keys of dataset. So we have target, description, target names, feature names, data, and file name. Feature names is the list of features in the data. Target names is the list of targets or classifier classes. And then target is just the target variable. So let's see the number of features, the list of features. So features, if you remember, we have sepal lengths, sepal widths, petal lengths, and petal widths. We have 4 features in this dataset. So the next step is a decision tree example in Scikit-learn. Please download the IPython files and open the template file and follow along. We're going to work with the iris dataset. As we have seen it before, you are familiar with this dataset. So this is true for all data happy coding in Scikit-learn. If you look at the iris keys, you're going to see the target, which is the target variable or the classes, and also feature names and data. Data are all the columns for feature variables in our data. The next step is to split our data into training and test. So to do that, we need to first import the function to do that. And then I'm going to split our data into training and test. I'm going to specify test size to be 20%. That means 80% for training. And also I'm going to specify random state to be any value, for example, 2. All right. So now we are ready to train and to develop our model and then train it. So let's import the decision tree classifier. So it's in the tree module from the Scikit-learn, and the name of the algorithm is decision tree classifier. All right, so I'm going to call my algorithm my tree, and that's going to be a copy of decision tree classifier algorithm. For now, I'm going to leave no parameters specified, so all the parameters are in their default setting, and we now can train our algorithm. All right, so as you see all of the parameters that the decision tree classifier has. We didn't specify any parameter here, so all of them are set up in the default values that they have. So the next step is to go ahead and make a prediction. So let's make a prediction. This is for test data, and I'm going to make a prediction also for the training data. Right? So to evaluate the performance of our algorithm, we need to import the accuracy score. And now we're going to print out the accuracies. And same thing for training data set. So as you see here, the accuracy of the performance of algorithm, the accuracy score is 93% for testing and 100% for training. It looks like that we have overfitting problem here. So
a decision tree example in
Scikit-learn, we're gonna
please download the IPython files and open the template file and follow along.
Pruning is a measure taken to
we're going to work
restrict
with the iris dataset. As we have seen it before, you are familiar with this dataset.
Do that by playing
and
with the parameters such as the max depth,
happy
the
coding.
max leaf nodes, and the mean samples leaf, as you have learned already. So let's actually develop another decision tree algorithm and to compare it with the first one and do some pre-pruning or pruning. So I'm gonna call this my tree 2, and that's going to be a decision tree classifier. And here I'm going to specify the max depth parameter to be, for example, equal to 3. You can play with this on your own to see the results. Okay, so our algorithm is ready. I'm going to train it on our training data. All right. So let's make a prediction. And also for the training variable, the training data, now let's print out the accuracies. And the same for the training prediction. So as you see here, the accuracy score on test data improved from 91%, 93%, and the accuracy score from the training data, the gap actually has decreased here. So we no longer have to worry about overfitting problem. Right, we can
a decision tree example in Scikit-learn.
If we can find it better.
Please download the IPython files and open the template file and follow along.
Smaller.
We're going to work with the iris dataset.
Here,
as we have seen it before, you are familiar with this dataset.
We still have
and
the overfitting problem. So
happy coding.
Now we have a bigger tree now. And again, the gap is larger. So the optimum value here, it looks like to be 3. We could also work with other parameters as well. But let's right now work on to figure out the feature importances for our algorithm. So let's print that out. Make sure to have the underscore at the end. So I'm going to do the same for our first algorithm that was suffering from overfitting problem here. All right. So here we have, as you see here, the scores for the 4 features. We have 4 features: sepal lengths, sepal widths, petal lengths, and petal widths. The 2 first features, the sepal lengths and sepal widths, are not important for the decision tree or splitting at all. So those are basically, if you want to go back to our games, those are not important questions to ask. But petal lengths and petal widths are important. If we print this out for our first algorithm, as you see here, it the sepal, one of the sepal values also important. So we have 3 features that are important. But this algorithm was suffering from overfitting, as if you remember. So you can also try to play with the other algorithm for pruning, such as the max leaf nodes or the min samples leaf, to see how we can control overfitting problem.
Decision tree splits, the iris example, behind the scenes. So we did see how the algorithm performance was, the accuracy score, and we could actually apply the pruning using the max depth limitation to avoid overfitting our algorithm in the second algorithm that we had. So now we want to see what really happens behind the scene. I mean, what features the algorithm really used, the decision tree, and also what conditions it used for splitting. So let's take a look at that. This is a figurative presentation of what happened behind the scene for the second example or second algorithm that we set the max depth to equal to 3. If you remember, for the algorithm, there were only 2 important features, the petal lengths and petal widths. The first 2 features, the sepal lengths and sepal widths, were not important for the second algorithm. So that's why we see here it only uses these 2 features. The first algorithm starts at the first node and it uses the first feature, the petal lengths. It looks like the petal length is even more important than petal widths. So it comes first as a first condition. So in this first node, we have 112 samples, and we have, these are the types of samples that we have for each class or category. So the first one is setosa, versicolor, and virginica. So here at the root node, we have 37 setosa, 34 versicolor, and 41 virginica. The dominant class here is virginica, 41, the majority. So the class is the dominant class is virginica. Now we're going to split based on this condition. Petal length less than or equal to 2.35. the algorithm has come up with this condition itself. If this condition holds true, we're going to come to here, true, then we have only 37 samples out of its 112 that these conditions hold true. And if you get the values, we only have from the Setosa class, 0 from the versicolor and 0 from Virginica. So this is a perfect classification, or this is a pure node because we only have one class here. On the other hand, if the condition was not true, if the petal length was not less than or equal to 2.35, we're going to go to the next node. So this is our split here. Out of these 112, we had 37 of them Setosa, which we classified here. So we are left with 75, which are 34 versicolor and 41 Virginica. The majority class or dominant class is Virginica here. So we're going to use the other feature, which is the petal width, to make a split here. This is the condition that the algorithm has set up, whether the petal width is greater than 1.2. If this condition holds true, we come to here. So we have 39 samples, 1 from versicolor and 38 from Virginica. So the dominant majority here is the Virginica class here. But as you see here, this is not a pure node or perfect classification. We have two actually classes here. But because we set up the limitation for the depths of the tree as number 3, so we are not going to split anymore. So we're going to fathom, and this is going to be a terminal node and a leaf. On the other hand, if the condition is not true, is false, we're going to end up with 36 samples, 33 versicolor and 3 Virginica. The dominant majority here is the versicolor class. But this is, again, not a perfect classification or not a pure node. But because we set up the limit for the depth of tree equal to 3, so we're not going to split anymore. And we're going to fathom this node, and this is going to be a leaf node. So this is how generally would work in the algorithm behind the scene. Let's now take a look at the advantage and disadvantage of decision trees, starting with the advantage of decision trees. Decision trees are easy to understand and interpret and visualize. Decision trees require little data preparation, no normalization required, as we didn't do in the example that we did. Decision trees can handle both numerical and categorical data, so they are very flexible and powerful. Decision trees are possible to validate a model using statistical tests. So this is more advanced that we don't have to go through it, but this is another advantage of decision trees. Now the disadvantages of decision trees. Decision trees, although are powerful and flexible, they are susceptible to overfitting problem. Usually create very complex models or tree that do not generalize well. So that means that the decision tree is usually susceptible to noises in your training data. Usually, decision trees need an ensemble of trees for better generalization. The ensemble of trees called random forest that we're going to talk about it later. Decision trees can be unstable, meaning we might have variance problem with them. Small variations in the data may result in generating totally different models. To avoid those problems or fix them, we can use bagging and boosting methods. Decision trees can create biased trees if some classes dominate. So if you have unbalanced data, then there's going to be a problem with decision trees. Let's see some tips on practical use of decision trees. Decision trees tend to overfit. If your dataset has a large number of features, getting the right ratio of samples to number of features is very important. Therefore, feature selection and dimensionality reduction can be helpful. The number of samples to generate the tree doubles for each additional level the tree grows. Therefore, try to control the size of the tree. For example, use max depths to avoid overfitting. or other parameters that we learn for pruning. More tips on practical use of decision trees. Use mean samples split or mean sample leaf to ensure that multiple samples inform every decision in the tree by controlling which split to consider. Try mean samples leaf equal to 5 as an initial value.